The next chapter is called as digital modulation. All right, now the data is digital. Okay, uh, so the modulation technique definitely needs to be changed, right? So when I say changed, it is with respect to the analog modulation schemes. If you remember the simple definition of modulation, right? You are trying to change the amplitude or the phase or the frequency of certain carrier signal, right? Or a high frequency carrier signal depending upon the amplitude or the normally it's the amplitude of the incoming message signal. There is a message signal. Depending upon its amplitude, you try to change either amplitude or the frequency or the phase of a carrier signal. The whole process is called as a modulation technique, right? So let's quickly write that statement now, because later on we are going to apply the same thing, only with a change that we are going to use a digital data or a binary data. Okay, right? Okay, so that means the the process of changing the amplitude or frequency or the phase of a high frequency carrier signal according to changes in the amplitude of a low frequency message signal is called as the modulation. All right, now you see, if the carrier as well as the message both are analog, it falls under the analog modulation technique. Okay, so if the message is digital, this implies we call the same modulation technique. In general, modulation technique refers to the analog only, right? But when the message is digital, uh, I'll write in bracket, it's not just digital or even the binary, because yesterday we saw that there is what is called as M-array system where you can have digital with multiple symbols, right? That's also considered as digital only. Okay, so if the message is digital or even binary, right, the modulation will be referred to as the digital modulation. All right, so recall what were the various simple fundamental modulation schemes we studied, right, in say analog communication or analog communication system, some subject we had earlier, right? So in analog, if you remember, we had one particular method, right, that is called as amplitude modulation, right? But here we'll write the equivalent one here, because input is binary but my carrier signal is still analog. Okay, so this is called as, right, in the digital modulation scheme, right, we have the first one is called as the ASK, right? ASK stands for the amplitude shift keying. So the it's not simple modulation now, it's a shift keying technique. So the digital modulation is fundamentally referred as the shift keying technique. All right. So the first one is amplitude shift keying. So as the name suggests, right, amplitude of the carrier is changed. Gets changed, right, according to the changes in the amplitude of the binary data or the message. Okay, similar to the frequency modulation, here we have the FSK. So as the name suggests, it's frequency shift key. So the frequency of the carrier. So we change the frequency according to the input signal, which is a binary or a digital form. Similar to that, we have a third technique. This is called as the PSK. Okay, so PSK was also under the phase modulation techniques, equivalently on the continuous modulation, right? So here P stands for the phase. Here phase in the sense the angle of your wave, right? So anyway, immediately after some time, I'm going to draw the waveforms for a given binary data, uh, which is which can be considered as ASK output, FSK output, and the third waveform will be the PSK output, so that you will understand. Okay, it becomes more clear. All right. So this is phase of carrier. It's altered as per the message. All right. Now, the fundamental idea here is that why the name shift keying comes into picture. That's also pretty interesting, right? You see, the most simple format of binary data is ones and zeros, right? So one means you are actually pressing a key, and zero means you are releasing a key. Let's assume, right? So there is a key. When you turn on, something comes in that's like on, like one. Turn it off, right? You don't get anything. The input becomes zero, right? So like that. So you see that some key is being pressed and released, right? Alternatively, to get the series of ones and zeros, right? So that's why the technique is called as a shift key. You are shifting the keys to get the inputs. So due to that input, either amplitude gets changed or the frequency gets changed or the phase gets changed, right? So that is done by the internal circuit, what we are going to write later. So the circuit will, as soon as the data comes in due to the keying, one of the properties of your carrier wave gets changed, and right, certain modifications will happen in the properties of the carrier wave, and you get an output, right? So that's why the shift keying comes into picture. All right, now very fundamental idea about the modulation is that, right, we always have the message is given to one part of the circuit called as a modulator, right? So we say this itself is a circuit, but actually this is not the complete circuit which is present inside the transmitter. But for the time being, for simplicity, this is fine. What we do, we try to send this, right, after the modulator, you give it to some antenna that will carry the signal to space. All right. Okay. Similarly, this will propagate through the channel, and on the other side, it will be received by a receiving antenna near the receiver, right? And this signal is given to another part or another circuit that is called as a demodulator. Right. So whatever operation that has been carried out inside the modulator will be reversed in a demodulator, and we get the message signal back. Okay. So this is a fundamental idea. But now the question is that when you have a message, why don't you send you the message directly and you get back your message directly? So that is our first question, right? Do you recall anything? Why don't you use this? Right? Why do you require a modulator and a demodulator when you can actually send the message directly to the space or directly to the channel? Yeah, think about that. Let's assume we want to transmit audio for certain distance. So we know that if we speak directly, the message can travel maybe 5 meters, 10 meters, right? After that, the noise will take over, right? Because there is what is called as a path loss, right? For every type of signals that you try to transmit, there is a concept called as a path loss, which is highest for these kind of naturally occurring signals. They face what you call as a attenuation very quickly, right? So that's the one point, right? So if you want to increase the what you call as the range of communication, you need to use high frequency content, right? That's what was observed initially, right? Because our speech is of very less in uh, frequency compared to the electric wave or the electromagnetic waves which we carry or the radio waves which we use, right? If you compare the radio channels frequencies, right? Let's say FM, right? It's how much? Around in 100 around 100 megahertz, isn't it? Right? But the speech what we write the before the telephone, right? It's limited within 4 kilohertz. That's the range in which we generate. So you see the difference, right? It's converted into a very high frequency content, and then you will send it so that you can cover the appropriate distance required for the communication. That's one thing, right? That's a major thing. And in addition to that, we have many other requirements, such as, okay, so I'll write the um, requirements. Why do you need, right? What are the desirable requirements to be met when we want to use the modulation schemes or modulation techniques? So the first one, as you told, you want to cover certain amount of distance, right? So to achieve distance of communication. That's the first one. Then, right? Now we'll slightly move from analog to digital because now we are looking at the digital. So whenever we say digital modulation, right, one of the performance parameter is nothing but the data rate, right? So because you are not sending the message as it is in case of a analog communication. Now you are converting into either bits or the symbols, right? Whenever that kind of data is being sent, you will definitely try to see that how fast it is, right? By looking at the data rate, how many bits will be sent or received, right, per second. Maybe it's bits per second, right? Bits per second is actually very small unit. So we will go for kilobits per second, megabits per second, gigabits per second, and so on. So you see the maximum to achieve the maximum data rate. That's another requirement here, right? If you don't convert it to digital and if you keep in the analog format and send, you may not be able to achieve the highest data rate. right? It will remain the constant, and it will remain same as the carrier's frequency. That's the maximum thing you can achieve. So if you come into the sampling part, it's actually half of that, because you always sample at a double rate to to satisfy the Nyquist rate. If I have 2 hertz of carrier, that will have only 1 hertz component of the message, correct, because of the sampling requirement. All right, then we have another very important parameter that is called as the transmitted power, right? You say I want to communicate, say, 100 kilometers distance without a wire. So I should have 2 antennas, one on the modulation, one on the transmitter side, one on the receiver side. So you see, I want to cover this range of communication with minimum power or maximum power. It should be minimum, right? So, right. So if you use the appropriate modulation technique, right, definitely you will be able to achieve the minimum transmitted power requirement. Power should be minimum. With the minimum amount of power, I should be able to achieve that. Means you should go for the modulation technique. Okay, so that's the next one. Minimum transmission power. Right. Then another requirement is minimum the bandwidth. So bandwidth is related to the communication channel through which you send the data, right? So this should be kept as minimum as possible. The reason is that when you have certain frequencies are available for communication, you want to put maximum number of channels over there, right? Channels carry the independent signals or independent messages. So in order to accommodate maximum number of channels within a given space in terms of frequency, you should have minimum bandwidth of each of the channels. So, okay, that's why it is minimum, right? Then you see this is very important. When it comes to the same example I told related to bandwidth, there should be maximum immunity for the interference, because I have certain bandwidth and I certain frequencies are available, and I put 10 channels within that bandwidth. So there should not be the interference between other channels with a particular channel. For example, I listen to a radio channel, means I'm expecting least interference from other channels which are very close to your tuned frequency, right? FM is able to achieve that, but if you move to the other modes of radio communication, you will, when you tune one channel, you will definitely hear slight interference of other channels as well. Okay, so that concept is maximum immunity. Maximum immunity to the interference. Okay, then one more very interesting aspect. Okay, we told everything, most of the points, let's assume, right? What if the circuit is pretty complex to achieve all of them, right? So then that's of no use, right? uh, anyway, people cannot invest a lot of money on a small uh, FM receiver. It should be very simple, very less complex, and minimum cost, then only people can afford. So that's the point. Next requirement, that is minimum circuit complexity and cost. Okay, and one more new concept we bring now. This is about the error. So in case of the analog communication, we never looked at the concept of error, because whatever was sent, similar format would have been received on the other side, right? Though you have the channel interference, channels attenuation, frequency selection, etc. Many parameters of the channel will affect the uh, data that is being carried through the channel, right? But you will see the effect of those parameters of the channel affect to the digital data, right? Slightly on a higher side, more there is more effect than the analog. That leads us to the concept of error, right? Error in the sense one is sorry, one is sent. Maybe the sorry, maybe the receiver will decide that as a zero, which is a error, right? Zero is sent. The receiver will decide that it's not a zero, it's one. So there is error. So we want to minimize, or I will say minimum probability of error. So these are the fundamental requirements uh, we have from the digital modulation techniques. All right, right. Let's move further. So we know now we are going to have a circuit for modulator, one circuit for demodulator. We'll see if the input is given in this format, how the output is obtained, what will be the equation of the, for example, ASK, what's the equation for FSK, what's the equation for the PSK. We also calculate most of the parameters from here. What is the data rate you can achieve, what's the frequency or the bandwidth required. uh, Circuit complexity cost will come into picture in the block diagram itself, so right, we will not worry about that. So one more very, the last parameter also we'll see in every case, right? Every modulation technique that we see will definitely look at the probability of error as a major point. Okay, we'll discuss definitely more about that. We'll also try to write the equation for the probability of error. Okay, if you use ASK, what is the chance of, right, making a mistake? We'll definitely write that. Okay, so we said that these are our requirements. So every cases we'll try to discuss about them. What happens to this? What happens to the bandwidth? What happens to immunity? What happens to complexity, etc. Okay, so but before that, let's try to do one thing. Let's try to plot the waveforms, right? Just to understand how the waveform is going to look like, right? Whenever I want to send a certain data. Okay, so let me assume that I'm going to send this particular signal in terms of this binary data. All right, so this is 1 0 0 1 0 1 1. So let me divide this into equal amount of space. So any digital modulation, one thing we observe that there is what is called as a duration of each of the symbol, right? Or in this case, it is bit, because every bit is sent separately. So there will be, right, a bit duration associated with it. So during the bit duration, according to your bit that you want to send and according to the modulation scheme that you are going to use, the waveform is going to change, right? Okay, now so this is for the bit 0. Then we have another bit, say 1, and the last bit, that's also 1. Okay, so this is the bit I want to send. Now, the first waveform that I'm going to draw here is corresponding to the amplitude shift keying technique. This is the time, and let me assume this is the ASK wave. Now, the amplitude of the carrier signal should change. Okay, so amplitude of the carrier in the sense whenever there is one, amplitude of the carrier is maximum in the sense it's it I'm normally you see if you remember the analog modulation schemes, what was the carrier used? What was the equation for C of t? Do you remember? What was the equation for C of t? So we used to assume, right? Whenever, let's say this is amplitude modulation, let the message m of t is equal to maybe am sine omega t, and let C of t is equal to something, right? If you remember, it's a sinusoid, right? Either sine or cos wave, correct? Right. So that means, right, correct. So you had a higher frequency FC for carrier compared to the message signals frequency FM, correct? FC much greater than FM was assumed in all the cases, right? Now also, let me write, say, okay, let me write in this way. So let us say, I'll write a equation for carrier here. Let's say the C of t carrier signal is equal to some amplitude, that is AC, into cos 2 pi fct, cos omega t, correct? 2 pi fct, right? In this, you see that fc is very large, okay? Whichever band you want to use, like you want to go for FM band, frequency modulation, that band, all the radio channels are present around 100 megahertz. So you see fc will be 100 megahertz. Okay, 2 pi into 100 mega, 100 into 10 to the 6 into t, into some amplitude you measure. AC can be 2 volts, 5 volts, etc. Okay, right. So that's this wave. Now in ASK, this wave is passed as it is whenever the symbol or the whenever the data you want to send is binary one. So that means it's a, if I say cos wave, okay, let me change to sine. That should make more sense, because normally when we write the waveform, it starts from zero. Cos means it should start from higher value, right? So for that reason, I'll write a sine. Okay, it's a sine wave. So that means, you see, let me assume a highest amplitude like this. Wherever you have one, it should reach a highest. The signal is passed as it is. That's all. Okay. The sine wave will be passed as it is. That means, so you see, it's a sine wave. So starts from zero. Okay. Now you see, it becomes a zero now. So as soon as the symbol becomes zero, you don't have to send anything, pass a zero. Are you okay? So zero has been sent. You see, it's zero. I'm not passing anything. But as soon as I get my next one, which means you pass your function once again, right? The sine wave, which you had assumed, right, will come into picture, right? Once again, I don't have to send, it's zero, because the symbol you are sending or the bit you are sending is zero. Once again, I have two ones, which means, right, you will pass the signal. So whenever it is one, it will pass. You don't have to change anything, simply pass. So this is the waveform of the ASK wave, right? Whenever zero, you don't send anything, it's completely zero, right? Like this. You see, shift keying happens, amplitude is getting keyed, right? One means amplitude is passed, zero means amplitude is suppressed. Once again, one means amplitude passed, zero suppressed, one, one. So you have amplitude being passed of the carrier, right? So we are not dealing, we are not passing the message as it is. You look at the C of t, and right, you pass it. So that's the ASK way, right? Let's go to the next part, which let's do the phase first. That's easier to write. So okay, let me, Let me write the PSK. PSK. Now, so PSK deals with the angles. Okay, the angle of communication, right? Communication in terms of angle of the carrier needs to be changed according to the amplitude of the message. Okay, so amplitude of the message now it's 1 and 0. So I need two different phases. Okay, when 1 is sent, you send one phase. When you send 0, you send another phase. Now, when how do you decide how many number of phases are required? That depends upon how many types of symbols you have. If you have like this case, it is a binary communication, very simple case, right? And in this case, I need only two phases because there are two symbols, or m is equal to 2, m array communication with the m equal to 2, that's a binary. So I need two phases. So how to select which phases, because you have so many, in the sense, how many number of angles are there? 0 to 360, correct? Out of which any one can be selected, but you will try to keep them as simple as possible. You always take one of the phase as 0 because you don't have to do any modification. Like you see here, the first signal, we have to use two types of carrier now. So C1 of t will be as it is, like AC into sine of 2 pi fct plus there is a phase coming up. You see this phase I am going to write 0, right? So you see that there is no phase allocated for this, no phase in the sense 0 phase. Okay, so 2 pi fct, this is the first carrier, but I need a second carrier C2 of t to send for maybe 0, correct? When 1 I'm going to send this, but when the symbol I want to send, or the bit I want to send, is 0, I need a different what you call carrier, right? So you see, divide the whole 360 into two parts, that's all. So one becomes 0, other becomes 180, isn't it? AC sine of 2 pi fct plus, simply add a pi to that, because you had 0, you added pi, you reached 180 degree. Once again you add pi, you come back to 0. You see, only those two phases will be generated because I need two phases, isn't it? So when your requirement is two phases, divide the complete 360 by 2. If at all you are using M array communication with M equal to 4, right, you will divide the 360 by how much? You will divide the 360 by 4. Are you okay? So that you get four different phases like 90, 180, 270 and 360. Correct? Right. So those are that's how the phases are getting generated depending upon how many levels of communication you are going to have. Now you see, for the first, whenever a first symbol, first bit is 1, so I'll send the C1 of t now. C1 of t is simply this. Okay, it's a normal wave. Start from 0, goes to maximum, comes to minimum, goes up. Goes up, reach a maximum and comes down. Let's assume this is the wave. All right. Now what happens? See, the second one has a phase change of pi, right? When I add 90 degrees to a sine function, it reverses the direction. Reverses the direction in the sense, now you see, this wave is coming down, right? It will not continue here. Instead of that, it will go up. That's the change of direction, right? Whenever you add 180 degrees to a sine wave, this is what is going to happen. Are you okay? So that's what I need to show here when I write the diagram. Otherwise, you just see here, what I should send is this waveform. That's all. So simply send the second waveform so that you are able to send the C2 of t. Sorry, I think my diagram got erased. I'll write it. All right, now I come like this. Now you see change of phase. This is the change of phase. The signal will not continue. Signal will be like this. But now there is no change. You see, it will continue as it is. Okay. As soon as it becomes 1, now there is a change of phase, right? I have to change it like this. Right. Now you see it's 0. Once again change the phase. So as soon as you have a change between 0 and whenever you have a change of symbols from 0 and 1, you need to make sure that you are changing the phase. Now I have 1, so this changes. Now I don't. Now you don't have to change. So there is no change of phase, right? So which all points you have change of phase, I'll just highlight. So there is a change of phase once again and once again, right? So at these points, symbols are actually changing. The bits are changing from 1 to 0 or 0 to 1. So you have switching between this and this. Hope this is clear, right? This kind of waveform you are trying to generate when you use the PSP. Okay, now let's go further. So the next type that we want to see is the FSK. So fundamentally, when I say FSK, I am expecting two different frequencies, one for symbol 1 and one for symbol or bit 0. So whenever bit 1 is transmitted, I use a particular frequency. Okay, but when I try to send the other bit, that is maybe bit 0, I have to change the frequency of the waveform to a different value. Let's try to write them what we are going to use for what value. We'll write that first. Say this is T, right? Let me use the two different carriers. So C1 of T is equal to AC. Now you see it can be sine wave, doesn't matter. Sine of, now you see 2 pi, I use F1 here. You see both the previous cases we had FC and FC, no change. But now I'm using, now I'm changing this F1T, okay? And the second carrier C2 of T will be equal to same amplitude, no change in the amplitude, right? Into sine of 2 pi F2T. You see F1 and F2 frequencies are changed. I hope this is clear, correct? Right. So let me draw accordingly. One, I'm going to use, whenever I'm sending one, let me use a high frequency component, frequency signal. When I want to send 0, I'll use a slightly lower frequency. Okay, let's say F1 is bigger, F2 is smaller. Okay, initially we are starting with a 1. So let me go for a high frequency component. So high frequency means more oscillations, that's all. Okay, so let me assume like this. Now I'm going to use a low frequency. You see, only lesser this thing. So this is also a 0. So use the same low frequency signal. Okay, as soon as you reach here, you see you get a 1, means I have to have more oscillations. Okay, so the change should be visible, that's all. It's not that you have to do it very uh, accurately. You see that this is lower, these two are high frequency, right? So whenever I have ones being sent, I'll try to send a high frequency. Now I have a 0 here, so let's just try to make it like this. Now you see you have once again ones coming up, so that should be a high frequency component. Signal should be of higher frequency. All right, now you see that there is a clear difference among all the three techniques. Okay, so one is the first one, ASK, amplitude shift keying. The second one changes the phase, right? Phase gets keyed up according to the message signal's amplitude. Third one is frequency is getting keyed, right? So that's why frequency shift key. Okay, any doubt so far? All right, so then we'll move on to, before looking at the specifications of each of these modulation techniques, right? We have one major design criterion, right? When it comes to the digital receiver. Okay, so depending upon what type of receiver you have or what type of demodulator you have, the modulation techniques are divided into two categories, two major categories. Okay, so that basically depends upon the detection technique used inside the receiver or demodulator. We can so for the time being, you can say that receiver is made up of only demodulator, no issue. Okay, so uh, the major difference is right in terms of availability of the carrier signal. Whether you have a carrier present, right? In the sense, let's say I have a transmitter, right? So I'll just write a single block diagram. There is a transmitter, and on the other side, I have a receiver. Okay, so you send something and you receive something. Now, so there is a message coming in, right? I'll write M, and there is a carrier C. Okay, so message, you do something with the carrier to transmit. Okay, this is X. X is the transmitted wave. It gets modified in the channel and it will be received as a Y. Let us assume. Now you see, if you want to get back your message, you have to remove the carrier component from this Y, right? Are you okay with that concept? No, I'm trying to keep the concept as simple as possible. I don't want to bring any mathematics right away, right? So I'm trying to say that the Y has a component of C because C plus M or something you did, M into C or M plus C, something you did to get this X on the transmitter side, depending upon the particular technique or the modulation scheme, right? I assume that I multiply, let's say, right? M into C is equal to X, let's say. It got modified during this thing, but there may be some changes in the amplitude or something might have changed by the channel. It reaches the receiver as a Y. Still, it has a, right? If you look at the waveform, it will still be very similar to X, not a lot of modifications. So in the sense, I need to, since I multiplied M into C to get X, so Y will be of the same format. I have to divide by C to get something similar to M, right? So let me call it as M cat. Some similar version of M will be I is what I want, which means, see, the receiver should know what is the C, right? Correct? Only when the receiver knows what C was sent, what C was used to do the calculation of X, you can use the same thing on the receiver side to cancel the effect. In the sense, you multiplied over there, you divide here. If you added M plus C to get X, so Y minus C will give you some M cap. Correct? So the point is, you should know the carrier. Right? Now, this is the major issue. Right? This is the major issue when the carrier is available, or the when I'll put it in this way: whenever the receiver knows about the information of carrier, maybe the amplitude, frequency, phase, etc., related to the carrier, that kind of demodulation or detection is called as the coherent detection, right? So the first one is, anyway, you will see that whenever we go for ASK, there are two techniques. One is coherent ASK, one more is non-coherent ASK. So coherent means the receiver has a clear idea about what carrier was used, right? Okay, let me write that first. Coherent detector or demodulators, right? Know the carrier used in, and just write TX, the transmit. Okay, which means directly you can use a C and you can do the calculation because it always knows about that. Okay, but let's say there is another type of receiver which is non-coherent. You see, in that case, this C is not available. There is no question of direct using of C, right? By looking at the received signal Y, you need to use a logic right? In the sense, logic in the sense, when it comes to circuit, you need to build a completely separate circuit, right? There is a part of the circuit which is responsible for identifying what C might have been used. Again, that is not perfect. Okay, whatever you guess, it not necessarily be correct, right? I might guess that, okay, maybe when I look at this Y, it looks like the carrier might be 250 kilohertz, but maybe it's true, maybe it's not true. So there is a complex, they are complex or complicated versions of the circuits, right? Of the detectors or demodulators, right? Uh, no carrier data available, right? On the receiver side, you don't have any idea about that. Okay, so right, this is something like there is another technical term being used, right? You might have heard of, if both transmitter and receiver know the details of the carrier, then we use a term, uh, okay, both are synchronized. Synchronized. Both know the same carrier, both use the same carrier forwards. But in case of the non-coherent, this uses a C. This the second one, that's a receiver, does not use a C. It uses a approximated version C cap, maybe. Correct? Are you okay? So that's the difference, right? Both the techniques are going to be used. They are still used, and right, the second technique, non-coherent, is going to be slightly complicated. Circuit will be complicated on the receiver side because you have no idea. You have to first derive what carrier has been used. Okay, so this is something like, if you are using the same communication frequencies always, then better to go with the coherent detector. At least circuit becomes easier. You like our FM, right? I know that my FM channel is minimum is 85, maximum is 105. I'm going to tune the channels only within them. So you have a coherent detector. My On the receiver side, you will have a coherent detector. You know what carriers might be used. But if you have a very wide range of frequency, or something like you are using, the best application could be something like the defense applications, where others have no idea, others should not have an idea about what frequency is being used, right? So it's actually non-coherent detector, right? So on the other side, right, you need to build, the circuit should decide, okay, maybe this is the frequency being sent, so you will try to tune to that, and then you uh, right, try to demodulate and so on, right? One very simple application I try to mention, but anyway, there are many more applications. We'll see later. Okay, so this is what is the broad class, right? It doesn't matter whether you are using ASK, PSK, FSK, or any other technique, right? Detector can be of two types: coherent detector, non-coherent detector. For both coherent as well as the non-coherent, the transmitter remains same. No issue with the transmitter, right? Transmitter is still same, right? Same transmitter works for both the demodulation technique. Whereas the decision device or the receiver is going to change, whether you, depending upon whether you are using coherent or non-coherent. Okay, so we'll move on to the first technique, that is called as the coherent ASK, amplitude shift keying, right? So we'll see how the coherent detection is going to work. Immediately after that, we'll look at the non-coherent as well. Right, irrespective of coherent or non-coherent, anyway, we understood that the receiver, the modulator or the transmitter is going to remain same. Right, now let us try to look at the waveform first, right? So let me say my message signal is in the NRZ binary format. Okay, so I'll write here. I'm directly writing, I'm starting with the block diagram. Okay, so So we'll start AHK with the block diagram of amplitude shift key. So we start with the message signal. In all the message signals, we assume that it is not available in the direct binary format, but after it gets converted into any of the data pulse shaped technique like NRZ, etc. So we keep one of them, we select one of them and keep it standard for all the modulation techniques, right? So that it becomes easier for us to understand, right? And do a comparison at the end. Okay, so that's why. So we'll try to keep restrict our discussion to, let's say, NRZ, binary data. Okay, now again, we are not talking only in terms of the magnitudes over here, because later on we are going to do the power calculation wherein the energy content of each of the pulse becomes important. Okay, so are you getting the point? We are not, I'm not writing the amplitude here, right? NRZ is 0 and A, right? A for 1, 0 for 0. Okay, that's what is our normal notation. But you see, right, the binary data means we are going to talk in terms of, right, the energy content. So what we do, it's a 0, right? 0 has no energy, and the 1 is going to have the energy or the level equal to root of EB. Okay, where EB is the energy content of the pulse that we use for sending ones. So sending one has, this has an energy equal to EB, and 0 has no energy. That is what is our the the meaning of this. Okay, so we now onwards we try to represent the data in this format, right? NRZ means 0 comma root E, right? Why exactly root EB, etc. I'll try to answer, right, as soon as possible. But as of now, just think that EB is going to be the energy, right? Something like a bit energy. So when I'm saying that I'm going to use a particular bit for this, right? What is the amount of energy that you are going to use will be denoted by this. Okay, all right. Now let me try to erase what I have written. So this is the binary data, right? And this data is passed through a multiplier circuit. Okay, but when it comes to the communication, the multiplier circuit is uh, called as a product modulator. That's a technical term, right? So we denote the product modulator by writing a X symbol over there. It's a multiplier, right? It multiplies, basically, we can understand that it's going to multiply two different signals, right? So if you try to recall what we had studied in case of amplitude modulation, right? You have a message signal coming from one side. So to that message, you multiply by the carrier, right? That was our concept. Here also we are trying to do the same thing, but you see, I have a slight modification. So here we don't write it as a direct C of t. Instead of that, we'll write this as a phi 1 of t. It's a phi of t, right? You don't have to write a phi 1 because there is no phi 2 coming into picture. Simply it can be just phi 1 or simply phi. This is going to have an amplitude. So if you remember previously, I just wrote C of t. The carrier signal is equal to some AC into sine function, right? Sine of something. This is what I wrote. Very similar to that. Now the carrier's uh, amplitude we try to write in terms of the bit duration, TB. Okay, this is necessary because later on when we uh, do the mathematics of the ASK's parameters, like what will be the PSD of this, how much power is required, etc. All those calculations, this kind of representation is going to be easier. Okay, so only for that reason we are trying to write it in this way. So the carrier signal is going to have an amplitude equal to, that is 2 divided by TB, the bit duration used, into cos that sign doesn't matter. Okay, cos 2 pi, you see, this is FC into T. Only the amplitude is what we try to write in terms of the TB. Anyway, it's going to be a constant ultimately because you selected TB. TB is fixed means this term will be fixed. Okay, so now I'll write the new name that we are going to use here. This is called as a product. In bracket, I write that I'm talking about this. Okay, fine. Now you see the output itself is called as the ASQ. So this is amplitude shift keying signal. What is it? So this is equal to, it gets multiplied whenever EB comes into this. EB comes means you have a product, 0 comes means no product. That's what we considered as our waveform, right? When we try to plot, that's what our waveform is. So this is equal to, now you see, this is the root of 2 times EB divided by TB. Okay, I'll use a capital for all. So root EB TB. So everywhere EB and TB, the B are capital, right? Into, this is cos of 2 pi FCT will be the output whenever the symbol is 1. Okay, and this is going to be 0 whenever the symbol transmitted is 0. So this is the equation of the ASK. Are you okay with this? Now you see, because of my output is either on, this is on, when 1, I have some output coming, whenever 0, output is not there. This is actually turning, circuit turns on, circuit turns off, depending upon your incoming signal, correct? Incoming signal is 1, output is there. There is output over here, right? At the same time, if the input is 0, right, there is no output. So circuit turns on for some time, circuit turns off for some time. Because when it is on, it produces an output. When there is no input, there is no output, right? So on and off, right? Circuit turns on for some time, circuit turns off for some time, because of which now you see we have a new name for this circuit. So that is called as on off key. Is a other name. So ASK is also called as this. Okay, now, so you see here, in case of a digital modulation technique, we have a new concept that is called as the basis function, right? In the sense, in order to generate your final modulated waveform, right, you use the specific type of the carrier. So normally the carrier, whatever you use itself will be called as the basis function, right? That is because it acts like a basis, because normally whatever the phi we are going to use, right? In this case, I see just phi 1 because I'm using only one carrier. But later on, we are going to bring multiple carriers also into picture. Okay, so wherein we may see phi 2, phi 3 also might come. Okay, so just before that, for the timing, let's try to recall that. Okay, right, this phi is called as the basis function, right? All right, let's use this basis function. You get used to the usage of the basis function once we discuss with the all the three, that is ASK, PSK, and FSK, right? You will get familiarized with this. But as of now, you see that okay, whatever carrier that we used to use in case of the continuous modulation technique is replaced by now what is called as the basis function. All right. So to to generate the ASK, we need one phi of t, right, called as the basis function. So basis functions are the terms used for carriers in case of the digital modulation techniques. Okay, there is another very important property for this phi of t, right? That is, it has unit energy. When you try to calculate the energy of this signal, that comes as 1. Okay, so this is just a note. We don't have to write in any of the answers, right? All the phi of t, right? The phi of t has unit energy. Why you try to keep it unity, right? We'll come to know later. I'll justify. Okay, now, so this is the phi of t, right? So I can write the phi 1 of t is equal to, I'll write the equation because so far I used it only in the block diagram representation. Let me try to write. So that is equal to root of 2 divided by TB into, this is cos of 2 pi FCT, right? And this is valid for 0 less than or equal to t less than or equal to capital TB. Only within this duration you try to send phi 1. Next, once again, you will give the phi 1 as it is, right? But you see that if the input is 0, output becomes 0. So I'll call this is equation number 1. And so anyway, I know what is capital TB, so I'm not going to write that. So it's a duration of each bit. All right. EB is the energy of each of the bits. So I think I should write that, right? Anyway, I'll write that later, right? So, and S of t, the output waveform of ASK is S of t is nothing but you either multiply by root EB into this phi 1 of t. So that's why we said in order to generate ASK, we need one phi of t. So that phi of t will be used directly as a product, right? EB into this. So you see that we are going to write this as root of 2EB divided by TB into the cos of 2 pi FCT, right? So here now I'm going to write what are the terms used. So what will be this EB, right? Transmitted signals energy per bit. So this is energy per bit. For one bit, how much energy you are going to send? TB is the bit duration. We need the term FC. What is FC? It's a carrier frequency. All right. So far what we understood is that whenever the we are using ASK and I want to transmit symbol 1, I'm going to, the circuit is going to generate this waveform at the output. And whenever there is no input, that is whenever the input is 0, S of t is also 0. Okay, right. So let me write that point here so that this becomes very clear when you read it again. So my next point will be, so this is something like the summary what we have studied. So if I am trying to send the symbol 0, that means the S of t equals to 0, right? Whenever you are trying to send the symbol 1, what happens? The S of t will be equal to root of EB into the phi of t, right? Now you see, right? Phi of t is there always, correct? So because the previous one could be also written as 0 into phi of t, that's why this becomes 0. Right, now you see phi of t is something like, right, I can consider the phi of t as a axis, like x-axis, x varies, y-axis, y varies, right? I can consider the phi as an axis and phi can be a variable, right? You try to relate, right? So initially it maybe you feel slight difficulty in the concept, but I try to make it easier by just giving an example like x-axis. What do you mean by x-axis? I have different values of x present over there. When I say x-axis, x is a variable, correct? Similarly, when you say y-axis, y is a variable. Now I am saying that this phi of t is a variable, right? Phi of t takes different values. Let us assume. Okay, so that means anyway, I'll first let me bring the coordinate axis into picture. So let me say, okay, I'll draw some here maybe. Let me call that this is my axis. So I'm going to call this as the phi axis. In this case, it should have been phi 1 because initially I think we brought the phi 1 into picture. Yeah, so it's a phi 1. So let me write a phi 1. Okay, so everywhere it's a phi 1 itself. Okay, I don't want to change. Right, so we started with the phi 1. Let's stick to that. This is phi. Phi 1 is my axis. Now you see, depending upon for it's something like if at all you used to write it as x-axis, right? Maybe, right, for symbol 0 you used to say x is equal to 0, right? They relate like this. When symbol 0 is being transmitted, my x value takes a 0. Whenever my whenever I'm trying to send the symbol 1, right, I'm making x is equal to root e. Okay, relate like that. That means on the phi 1 axis, I can actually mark two different points, for one for symbol 0 and one for symbol 1. Correct? Are you able to relate that? That's why. So I'll write another point here. This makes things more clear. So therefore, the coordinates of, right, 0 and 1 can be written like this. So if you have 0, right, so I'll write for symbol 0, I'll write one coordinate. For symbol 1, I'll write another coordinate. You can say like x1 equal to 0, x2 equal to root e. It's still same, right? Because they are two different points. That's all. Correct? On the x-axis, the first value denoted by x1, it's 0. The second point I try to denote it as x2. That is equal to root e. Anyway, we are not going to use this x and y notation. So for just understanding purpose, I go to it. All right, so let's move further. So the coordinates, in the sense, I should be able to mark it. So first let me write for symbol 0, I'll give the symbol s. It's a symbol 1, I'll denote it as s1. That is denoted by root e. Okay, and for 0, I'll call it as s2. That is equal to 0. So now let us try to mark. So you see, we made one comment earlier saying that I need only one basis function, right, to generate the ASK, right? The same thing I can actually convert it in another format. I can make the statement in a different way now, saying that, so the ASK signal, it can be represented on a one-dimensional, it's a one-dimensional signal, I can say, in the sense, when you use only phi 1, like only the displacement you are measuring. Let's say there is a vehicle moving in a straight line. So you see how many coordinates you need to mark the distance of that vehicle with time, right? So at t equal to 1 second, it is located here. T equal to 3 seconds here. T equal to 8 seconds here, and so on. You see, you are filling up only one axis. So that representation becomes one dimension. All right, very similar to that. Now you see the whole function, whatever we are writing, that is ASK signal, can be represented by using only one coordinate, that is phi 1. So phi 1 takes two different values whenever signal is 0 or 1. Again, I have to only two values. I don't have to write multiple values. So only two values are there. So that means, let me try to write like this. So this is, let me say this is S2, that is equal to 0. And there is a S1 somewhere here, right? Which is equal to root of EB, right? So S1 corresponds to signal 1, S2 corresponds to symbol 0. Okay, now what is the use of this? Why do you want to write like this, right? So the answer is, it is easier to uh, decide, right? Decide how to design a receiver by using this kind of diagram. I'll tell you the answer now. So let me say somewhere at the middle, I'll draw a point. Okay, if this is 0 and this is EB, what will be the midpoint? Midpoint should be root EB by 2, correct? So there is, draw a line, vertical line, root EB by 2. So this is where I write the midpoint. So between the two lines, that is root of EB divided by 2. Okay. Now you see, because, so I am supposed to send this particular signal, right? Whenever I want to send 0, right? From the receiver side. Sorry, not from the receiver, my mistake, from the transmitter side. Sorry. Okay, right? I'll send this particular coordinate, right? Whenever I want to send 0 from the transmitter, and I will send the value corresponding to this point whenever I'm trying to send symbol 1 from the transmitter. Okay, but you see, when the signal propagates through space, through the channel and comes to the receiver, the 0 might be somewhere received, maybe here, okay, because something has been added up to the signal so that it reaches here, okay, or the one which you have sent, right, maybe its amplitude got reduced and it reaches, it is, this is what is received, let us assume, okay, this is received for 1, and when you send 0, this is what is received, right? So it's not what has been sent, correct? You are not in either of the cases, you are not receiving whatever that has been sent, correct? Right. Now you have to tell the receiver how do you make the decision, right? For that purpose, this particular graph becomes easier to understand. What you do, divide the complete space into two parts. Anyway, I'm not going to receive a point here, okay, because it's not two-dimensional, it's a one-dimensional. Whatever you receive will be on that line. Sorry, my mistake. Just, yeah. Whatever you receive will be on this line. That's for sure. Okay. On whatever you receive will be present on this axis. Always will be present on this one dimensional or that particular phi 1 curve. Okay. Now, so that means I have to divide the whole axis into two parts. Let's try to divide that. All right. So this is how it's going to be divided. Okay, this is one region. This on the other side, I have another region. This is the other region. Okay, so this is, I'm going to call it as a, say, this is region 1. Okay, I'll call it as a, I'll go with the textbook notation. Textbook calls this is region Z1, right? This side is region, I think Z naught is used. Okay, Z naught for Z. Now, so which is the decision boundary? That is root EB by 2. Whenever I receive a value which is here, here, or anywhere, right, on the left side of root EB by 2, the decision is easy to make, right? Saying that, okay, that is symbol 0. Okay. Whenever you receive something, right, that is on the right side of root EB by 2, right? So that means it falls under region 1. Any point that is on the region 1 will be classified as symbol 1 by the receiver or the demodulator. So just to analyze this purpose, we write these kind of representation, right, on a graph, right, by using the basis functions as the axis, right? So if you use only one basis function, that means it is one dimensional, right? I need only one dimension to represent this on a graph. There is a name for this graph. This graph is called as the signal constellation. Signal constellation of AST. So, which means definitely we are going to write various constellations for other techniques as well, that is PSK, FSK, and so on. Okay, we understood. So far it is fine, right? We understood that, okay, this is how the representation is going to work, right? Okay. So now let's move further. So from this particular signal constellation diagram, the distance between the message points, what is the distance between S1 and S2 equal to EB, because one is at EB, other one is at 0. So, right, we have the gap between the 2 points equal to EB itself. So what is the decision boundary? It is the midpoint of them, that is equal to root of EB, right? So basically we observe there is a segmentation that is happening on the phi 1 axis. So Z0 region will be corresponding to symbol 0, right? Right. And the Z1 is the region that is corresponding to the symbol 1. Is it okay? Okay. Now, all right. Now, whenever we are using the signal, let's try to look at the power spectral density of this ASP. Okay, that's the next topic, because we want to look at how much power you are going to put and at what frequency. So we have to check that as well, right? So let's go for the next topic, that is PSD of ASP. Now we have what is called as the S of t given, right? And that S of t, let's try to represent that using, right, because it passes through, I'm multiplying that phi 1 of t into the binary incoming signal, right, that is NRZ format. On the frequency domain, I am actually writing the ASK's, what you call a PSD, right? So because I am writing the PSD of the total, let's show you the diagram once, right? I'm trying to write the PSD of this. Okay, so directly we write this. Now you see, if you try to represent the baseband signal, right, that is represented in the NRZ format, the power spectral density of that signal, let's try to write. Okay, so baseband signal is what I'm trying to write. Right, this is what we know now. So we know that the PSD of the NRZ baseband signal, right? That is what I'm trying to write now. We already have derived this in the previous chapter. So let's directly write. That is S baseband, okay, of F. NRZ format I'm trying to write. If you look at this, there is a square divided by 4 times delta of F plus A square TB divided by 4 into sync square. Okay, FTB. Same thing we have had derived earlier. So if you are not able to recall how do you get this, right, just refer back, you will get the answer. All right. So this is the power spectral density of your incoming signal. Okay, incoming signal in the sense that's the one which I just now showed you, right? I'll go back to the same diagram just to understand what exactly is that. That's the PSD. I'm talking about this. So what you are trying to do next is that this PSD is getting multiplied by the cos function, root of 2 by TB into cos sum. Okay, so whenever you are being multiplied by a cos function, what exactly happens to the baseband is that it's no more baseband signal, it becomes the band pass signal. Have you heard the word baseband, band pass, etc.? Right. Can you tell me a difference? Baseband, I think I already have answered you somewhere, maybe earlier, but band pass mostly we have not used so far in my class. Okay, so uh, try to recall if you are able to answer that. That's well and good. So let me repeat quickly. So we had a baseband signal, right? That is going to look like this. We want to make it a band passing because I want to move my low frequency content to a high frequency content, right? So low frequency content is this one, which is represented in this format using the power spectral density analysis. Okay, so that is denoted by SB of M. But in the block diagram representation, we saw that there is a high frequency component that is represented by the phi 1 of t that has a frequency fc. So that means my low frequency signal will be moved onto this location. If I try to represent this as a triangle, right, triangular waveform, this becomes like two triangles, right, centered at fc, right? Ultimately, that's what I'm trying to do by using the product modulator. Is it okay? This till here? Okay. Now, so directly let us write the ASK signals, what you call the power spectral density then, right? I just have to repeat the PSD of this at two locations, one at plus FC, one at minus FC. That's all. That's what is the whole concept is all about, right? How to write the PSD of the ASK signal. I just have to remember what is the PSD of the NRZ binary data, right, which was already derived in the previous sessions. Simply copy that at two different locations decided by the frequency of the phi 1, right? So directly we can write the answer. So that means I just have to repeat uh, which waveform. I have to repeat this waveform at two locations, one at plus FC, one at minus FC to get this. So that's the final answer. Directly write. Let me write it. So let me write one more point here. SB of F is the baseband, correct? So this implies, so that's the power spectral density of the NRZ unipolar format baseband signal. Right. Now you see, since I multiply this with the phi 1 of t, right, the PSD becomes a band pass signal, right? So therefore, okay, I can write in this way, uh, by multiplying NRZ format with the phi 1 of t, right, we get the ASK as a band pass signal, right? Whose PSD can be represented, whose PSD can be given by. So I'll call that as S of F. You see, I try to write using the standard format. So this is, since there is a sinc square, actually this becomes 1 by 4 times. So S of, that is SB of F minus FC, one component getting shifted to right, and another component, that is SB of F plus FC. So F minus FC, as you know, that is the right shift. Okay, one which moved to the right, correct? So this is moved to the right side. That is F minus FC. Similarly, this moved to the left, right? So that is the F plus FC. There is a left shift of the this signal, and there is another copy of the same thing shifted to the right. I hope that is right. Yeah, the 1 by 4 is a scaling factor, right? So it's coming from the scaling factor. So normally when this happens, amplitude will not remain same. Okay, this amplitude is different than what is the original. Magnitude will not remain same. All right. So because of that, you have this 1 by 4 coming into picture. This varies from, this is again, this is when I'm talking about the PSD, power spectral density, there is a coefficient 1 by 4. If you are looking at what is called as the spectrum, there is a different multiplier. Actually, there is a completely different derivation for that. So as of now, we are skipping that part. Okay, that's not required because we are not dealing with how to represent the PSD, etc. So directly use this equation and substitute. All right, it's a standard equation to write, convert a it's like a baseband PSD to a band pass PSD. Okay, SB is baseband PSD, SS is the band pass PSD. So to convert that, this is the equation, which means I have to substitute the SB of F over here. So let me write this equation. This implies now SS of F is equal to, there is a 1 by 4 into, so what you write? First you write the SB of F with F being replaced as F minus FC. So that is A square divided by 4 into delta of F minus FC, right? Plus the A square TB divided by 4 into the sinc square I'll write here. This is F minus FC TB. Okay, this is the first part. There is another part coming, right? So plus, that is, once again, SB itself has to be written, SB of F, but every F is to be replaced with F plus FC. Are you okay? So that means, once again, this is A square by 4 delta of F plus FC plus A square TB by 4 sinc square of, this is F plus FC. So now you see I have the components like this. Now let me write the SB of F once again, because that's what I'm going to use to plot the final graph. Right. So let me draw that. So this is F, and let us say this is my y-axis. I'm plotting the SB of F here. We know something already about that. There is a delta function, right? That is delta of F. Okay, so this is the delta function. So this is A square by 4 into delta of F. All right, then A square TB by 4 into sinc function, sinc square function. So sinc square means it is only positive, right? It's not sinc. So I think I made a mistake when I wrote here, because what I wrote was a sinc function. You see, it has negative parts as well. There is no negative, okay? Only positive because it is sinc square, right? Whatever you have negative becomes positive. So I should write that very properly now. So it starts from here, goes to this point, it comes to the top, and like this. So same thing should happen even on the other side. This is the sinc square function. Okay, so if you remember, this was 0, this is 1 by TB, this is 2 by TB, minus of 1 by TB, right? Minus 2 by TB, and so on. This is what we had at our original place, right? So this has actually an amplitude that is equal to a square TB by 4. Okay, that's corresponding to this. Okay, so this arrow mark what you see here is corresponding to the delta function whose magnitude is a square by 4. Okay, that's fine. Now let's move to the SS of f. That's what we see over here, right, in the equation format. I'm trying to plot that. Okay, that means I need a larger axis. Okay, so this is the f axis. Let me take a point. Anyway, I'll take the same thing as my point. This is what I'm trying to plot, the SS of f. Now you see, you will mark a point called FC and another point called minus FC. Now around this, the waveform needs to be shifted. Okay. Now you see this moves to right around FC. So there I need to mark a delta function. So mark a delta function over there. This has to be, what is the amplitude of this uh, delta function? Can you tell me? Look at the equation. What is this one? You need to look at the equation of SS of f. So it's not visible. I'll slightly. Okay, now check this. What is the amplitude of delta function? Delta function is this, right? A square by 16, isn't it? So f minus fc is on the right side. So this is a square by 16 into delta of f minus fc is this one. So you see there is a change in the uh, amplitude. Previously it was a square by 4. Because of that multiplier it reduced. Are you okay? So that is a square by 16 delta of f minus fc. Similarly, on this side, I still have another function to write, that is a square by 16 into delta of, this is f plus fc. Are you okay? That's the other term I'm writing from. Okay, multiplied by the 1 by 4. Okay, now we need to write the remaining part. One is the shifted a square tb by 4 sinc square to the right, and one more term, the same a square tb by 4 shifted to the left by FC. So let's try to write that. So I will try to start it from here. Start from here, reaches a minimum, maximum, minimum, and so on. So same thing on the other side. It comes down, minimum, and maximum, and so on. Same thing. Try to write. I'll try to write over here. Start from here, goes to minimum, maximum, and so on. So same thing. Like this. Okay. Now let me mark down the values and the equations. So what is the equation of this waveform? This is going to be a square by 16 into the sinc square function of, what is that? This is, write a bracket, f minus fc into tb. Are you okay? F minus fc because it is shifted to right. Similarly, right, what is the equation of the one which is shifted to the left by fc units? That is this one. That should be a square tb by 16 into sinc square of, this is f plus fc times tb. Are you okay? Now, so again, every point will be shifted to right, means it is getting added by a point. So this becomes FC plus 1 by TB. The other point becomes FC plus 2 by TB, because original point was 2 by TB. This is FC minus 1 by TB, FC minus 2 by TB, and so on. So other point will be minus FC plus 1 by TB. This is minus FC minus 1 by TB minus FC minus 2 by TB, and so on. We can write out. Now you see this, the one which we see here is a baseband, right? Now you see here is a, whatever you see here is the band pass, right? So in the question, if they are write the PSD of ASK signal, you need to answer this part. Okay, the SS of F is what we are supposed to write. So when the PSD is going to be asked to be plotted for the given ASK.